Hi folks, welcome back to Physics with Captain Rod. Making this video here to help you out with Chapter 6, number 25 in the OER College Physics text. So the problem is kind of described in this picture. There's a car or a vehicle that's moving in some sort of circular track. Some things to consider about this problem. One, it doesn't say anything about changes in speed. There's no changes in height, anything like that. So this is just not a work energy problem. This problem is not about work and energy, which means it's going to default to Newton's second law. I mean, when you're working problems in physics, there's really kind of three categories, or at least if you're in my classes, there's three categories. You've got problems about motion, where we typically draw a velocity graph and use concepts of slope and area to analyze it. Then you have Newton's second law, where you draw free body diagrams and write Newton's second law equations, and you got principles of work and energy. So which of these three you use, you have to decide kind of on a case-by-case basis. So if this is not a work energy problem because there are no changes in kinetic energy mentioned, there's no heights, there's no anything like that. It's also not really a problem about motion. It doesn't say anything about, the car moves a certain distance in a certain time or anything like that. There's just no motion variables mentioned. So this is going to default to Newton's second law, which means you need a free body diagram. Now, if we're going to draw a free body, it's important to understand what type of free body to draw. One possibility is kind of a top-of-view free body. Now, if you notice the problem, if you read it, it says something about ideally banked, right? So the word banked is important in this problem. Where this car is, this location here, it's on a banked type of curve. It's not flat. It's not like I have it shown over here. So if it's banked, that means that if we look at this problem from this perspective, like looking at the car coming right at us, what we would see is that this thing is looking maybe something like this. That's what they mean by banked. And when it says ideally banked, it means that the car can take the curve even if it's really icy or no frictional force at all. So ideally banked means that you do not need a frictional force to take the curve. So what you want to do now is draw a free body diagram of the car. This would be a really good perspective. There's no frictional force because of the terminology ideally banked. And then ask yourself, where's the gravitational force vector go in that free body and the direction? And then we have contacts here and here. Now we normally describe those with a normal force. Now I'm not going to draw this because this is your homework, but you're going to want to put the normal force in. And that's pretty well it. If we leave out any sort of frictional forces, that's all you'd have in that problem. So put those force vectors acting on the car. Then you have to write some force equations. Now remember, Captain Rod's rules of thumb, carrots that I call them. One of them is identify the acceleration direction, call that positive. In this problem here, this car, this is a constant speed example. So the magnitude of the velocity, constant, not changing. So there's no tangential acceleration that's relevant in this problem. However, the car is undergoing circular motion. Right, so there's a specific type of acceleration relevant for that. I will go ahead and draw that. The acceleration vectors, centripetal acceleration vectors, always point towards the center of curvature, and they have a magnitude of v squared over r. What you need to do is recognize this acceleration vector towards the center of curvature. Over in this picture, what direction is that? And then write yourself a force equation in that direction. You can also write another force equation at a right angle to it. So you should be able to write two equations from your free body here. And that should be enough to answer this, to get this problem done. Again, the intention here is not to work it for you. I just want to give you enough hints here to get you going so you can successfully get this done on your own. So I hope that does that. If you have any questions about it, call or email. Have a great day.